This video goes along with number 36 from the final review packet. We are going to write this expression given to us as a single cosine with a phase displacement. Now on the formula sheet, it's not super obvious which one to choose because you're not going to see that phrasing, single cosine with a phase displacement. That's what this right-hand side is, right? That's a single cosine over there. Here's our phase displacement, but the kind of language that's used on the formula sheet describes the other side, which this is a linear combination of cosine and sine. So that's how it's described on the formula sheet. Okay, so just be careful there that you can find the right formula. Now, one thing to note, in the on the formula sheet, the term in front of b or the term in front of cosine is the b value, but do you notice these are switched? This one has sine first, then cosine, where in the formula it's the other way around. So I'm going to, first thing, let's just rewrite our equation or our expression here so that it matches what we're working with. And I guess I'll put thetas instead of x's. Okay, so now that we have that, we really want a diagram to go along with this, because once we have the diagram and a little triangle that comes out of this, all we are really looking for is the hypotenuse of the triangle. That would be A. And the angle in standard position that goes along with that triangle, that would be D. These coefficients are the lengths of the legs. Cosine always goes with x. So 12, positive 12 in the horizontal direction. So let's just pretend that this length is 12. And then positive 5 in the vertical direction. Oops. So we're looking at this triangle right here. And what we're trying to find is A, the length of the hypotenuse, and D, the angle in standard position. That diagram is super important because especially if we had any negatives thrown in there, we may be in other quadrants. Like it's possible that you could land down here and you would want D to be this angle. Okay, so just keep that in mind as we go through and actually calculate that. Now, A just comes from the Pythagorean theorem, or if you know your triples well, A is just 13, so you can work that through. D can be found by, you could technically use sine, cosine, or tangent, but best practice is avoid using your own answer if possible. So if we look at this triangle, we would say, okay, tangent of D equals opposite over adjacent, 5/12. So D would be, we are going to keep in mind that we might want arctangent instead of just inverse, because we may have to adjust that measure to fit the quadrant that we're in. So let's put in, right in the calculator, inverse tangent of 5/12, but just know that we might need to add 180 to it. We're not forced to do that, but we may need to adjust it. Now, when you enter that in, you get 22.6 degrees, which clearly is in quadrant 1, so we don't need to add the 180, but for some reason our triangle was down here, we would be adding 180 to that to put us in the proper quadrant. Okay, so let's go back up to where we were here. We have A, we have D, let's plug them in. So the single cosine with the phase displacement looks like 13 times cosine of, I'm going to use theta since we had theta there, theta minus 22.6 degrees. Here's a great way to double check your work. Graph both of those. Graph the left side, graph the right side. They may be a smidge different because we rounded this angle, but they should nearly, if not perfectly, coincide with one another.